Hi, my name is Tedjopurnomo, and I will be presenting the paper Equitable Public Bus Network Optimization for Social Good, a case study of Singapore. Public bus transportation has many benefits. It reduces air pollution, it improves community mobility, and it reduces road congestion. However, existing public bus network optimization are focused on improving efficiency, neglecting the important equity factors. Public transport inequities are prevalent in many cities around the world. For example, in Perth, Australia, 70% of the population share only 30% of the bus services, with the elderly suffering the most from this inequity. This value drops to only 19% in Melbourne, and in London, it is found that people with no educational qualification have worse public transportation inequity. There are three main challenges in equitable public bus network optimization. The first is that the defining of efficiency and equity metrics. Bus efficiency is not just about creating direct routes. It is also concerned with the scheduling of the buses and also the routing of the buses to minimize waiting time and minimize the number of transfers. In addition, designing the equity metric is also a difficult task because we need to find the correct level of granularity from individual level to group level. The second challenge is that there's a trade-off between route equity and directness. To improve equity, we need to route the buses to areas that are underrepresented. However, doing so may result in longer, less direct routes, which will reduce the route directness and efficiency of the network. We need to find a good trade-off between the two, which is not a simple task. And finally, the third challenge is that bus network is constrained by the resource available. The number of available buses are limited and the operating cost of those buses will need to be minimized. In our work, we seek to formalize the problem of equitable bus network optimization and explore the difficulties of this task. Since our work is the first of its kind, we curate the first equitable public bus network dataset based on Singapore. We then analyze the bus network equity through several choices of equity metrics, each with their own strengths and weaknesses. We also study and discuss the efficiency of bus networks through our novel efficiency metric. And finally, we perform exploratory experiments using several case studies to show the intricacies of bus network optimization. Our dataset consists of several components. First, we have a bus network which consists of a directed graph with road junctions and road edges. We have a set of bus routes complete with the bus stops and bus schedules data. And then we curate two distance matrices for car and bus travel distance based on these previous two data. Specifically, this distance measures the shortest car or bus travel time between every pair of bus stops. We then use the census boundaries data to identify Singapore's 55 planning areas, which allow us to analyze area and demographic level efficiency and equity. Finally, for the equity aspect, we utilize Singapore's demographic data to identify three sensitive attributes of age, income, and qualification. Our efficiency metric captures both travel efficiency and travel convenience. Travel efficiency has to take into account four factors: route directness, service coverage, network efficiency, and the number of transfers required. To capture the efficiency of the bus network, we compare against the gold standard, which is the car travel distance. The car distance between two bus stops is calculated based on the road network using the A-star algorithm. This does not take into account the waiting time or transfers associated with bus travel, which is why this is the shortest distance possible. The closer the bus travel is to the car travel distance, the more efficient the route. To calculate this efficiency metric, we first need to calculate the stop-to-stop bus travel distance and then the stop-to-stop car travel distance, which we will then aggregate from bus stop level to area level. Finally, we divide the car travel distance with the bus travel distance. Since the bus travel distance will never be smaller than the car distance, the largest efficiency value is always going to be 1. And this results in a metric that is easy to interpret and use. For example, a value of 1 means that bus travel is as efficient as car travel, and the value of zero point 0.5 means that a bus travel is half as efficient. We also capture the travel convenience. Convenient travel is a travel with less waiting time and fewer transfers between trips. We use the concept of a transfer penalty that captures both of these aspects. In Formula 2, we convert the bus waiting time to what's called a waiting distance, and this allows us to add up the waiting time with the travel distance to create a unified metric. We also incur a transfer penalty based on this waiting distance. Each transfer should be penalized heavier than the previous, which encourages fewer transfers between bus stops. In our work, every subsequent transfer incurs double the penalty, as denoted in equation 1. In our work, we propose 5 equity metrics. Some of these metrics are based on the comparison between advantage and disadvantage areas, and this is determined by comparing the area level disadvantaged population with the countrywide percentage of population. The 5 metrics are population scale equity or PEQ, area level equity or AEQ, maximum difference or MD, standard deviation or SD, and residual difference or RD. Firstly, the PEQ metric calculates the efficiency discrepancy for advantage and disadvantaged populations. On the other hand, AEQ calculates the efficiency discrepancy of advantage and disadvantaged areas. Unlike the PEQ and AEQ metric, the next two metrics, MD and SD, concerns the spatial distribution of bus resources rather than demographic distribution. In particular, MD measures the difference between the most and least efficient areas, and SD measures the standard deviation of all areas' efficiency. The RD metric fulfills a different purpose. In regression analysis, this metric is used to measure the extent of over or underestimation discrepancy between advantaged and disadvantaged groups. In our work, we use it to evaluate how equitable the bus optimization algorithms are in terms of how they improve or degrade the efficiency of advantaged or disadvantaged areas. In summary, our 5 equity metrics are population scale equity or PEQ, which compares the bus services of advantaged and disadvantaged population; AEQ, or area level equity, which compares the bus services of advantaged and disadvantaged areas; maximum difference or MD, which compares the most and least efficient areas; standard deviation or SD, which compares the overall service level of all areas; and residual difference or RD, which compares the way bus network algorithms treat advantaged and disadvantaged areas. Using this metric, we performed several experiments and case studies. We used the Singapore dataset with 55 planning areas, 361 bus routes, and 5,021 bus stops. Using this dataset, we compare our models with generated routes. To do this, we first define what's called a ground truth network by using the existing network of 361 bus routes. We then randomly remove a quarter of the routes, resulting in 207 bus routes, which we call an initial network. Next, we feed this initial network to our bus network optimization algorithms, which will then generate the quarter of route that has been removed, or 90 new routes to be added to the existing network, subject to resource constraints. Finally, we can compare the efficiency and equity of these generated networks with the ground truth network. For the comparison, in our work, we use 3 simple heuristics. The first is the direct method, which directly builds routes between a set of 4 selected bus stops using the shortest path possible, and adds all the bus stops that it passed along the way to create one full bus route. The gradual method selects a pair of starting and ending bus stops and builds the route by adding one stop one by one from the start to the end. And the gradual equity method does the same thing as the gradual method, but takes into account the equity factors. The experimental result is as follows. There are several important observations. The first is that the population scale equity and area level equity are all nearing the ideal value of 1. This means that advantaged and disadvantaged demographics in Singapore receive similar levels of public transportation quality. However, the MD score is noticeably lower, signifying that the spatial distribution of Singapore's buses are less equitable. The second observation is that all baseline methods did not manage to outperform the ground truth. In our paper, we use several case studies that explain why these simple heuristics fail to outperform the ground truth, which is the human-generated routes. And this, in turn, also explains the difficulties and intricacies of bus network optimization. Finally, we can see that all baseline methods tend to improve on the equity aspect based on the MD and FD metrics, signifying that these methods are able to provide a better spatial distribution of Singapore's bus resources. And with that, this is the end of the presentation. Please read our full paper for more detailed explanation and case studies. These are our list of references, and thank you for your attention.